This video is being sponsored by 𝗣𝗥𝗢𝗣𝗪, which has a collection of well-written crafted courses for software developers, from Python to front-end to system design to scalability to Docker and whatnot. Learning at 𝗣𝗥𝗢𝗣𝗪 is really powerful because they have all coding workspaces in the browser itself, and also they offer 𝗣𝗥𝗢𝗣𝗪 Unlimited, in which you pay only once for all the courses. They have annual and monthly plans, and my audience gets a 10% additional discount on the 40% campaign they have for India. So you get a 46% discount on using the coupon Rachit, and you can have the link in the description below.
Last time we discussed one log structured based storage engine, and we discussed how it's really good and it's being used in production storage engines, but it faced certain limitations. So today we will be discussing about LSM Trees, which is being used by a lot of big companies like Google and Facebook in their internal storage engines. Like RocksDB, this is also open source. Cassandra also uses it, Bigtable uses it, and the idea for these videos, making these videos, right? The basic idea is simply for you to develop that understanding so that you can go ahead and create further deep down roots into how these storage engines work internally. So when the reads are coming, when the writes are coming, how is the database exactly handling it and storing it in disk? Is it doing some like in-memory caching kind of thing layer in between, whether it's storing and pooling all the writes and only then persisting it to disk after a certain point of time? So how these storage engines work, we will develop a clear understanding of that in this video. And then once we do the same thing for page-oriented or B-trees, I am sure that for almost all databases, now you will be in a position to actually go and study like advanced textual tutorials and documentation, and now you will have a better sense of how they work and what are the problems they solve, right? So today we'll be using something which are known as log structured merge trees, and they are used in a variety of like really huge databases which are designed by really top 5 product firms like even Google, Facebook. They have designed something like Bigtable, RocksDB, and if you will go to the Wikipedia of this page for LSM trees, you can clearly see that they are used by something like Apache, Bigtable, HBase, LevelDB, RocksDB. So RocksDB is by Facebook, and I happen to have used this in production. So it's really fast and the write performance is really great with LSM trees. So this will not only solve the problem of keys, but even the range queries are really good with this. But they are essentially having the same key value kind of storage, but the keys now are sorted. They are not in any haphazard fashion. The essence of LSM trees is based on the fact that the keys are always sorted. So we are incurring some cost to maintain this sortedness of the table or the storage engine. Now essentially you can break down an LSM tree into 3 parts, which is a mem table, then there is an index, it is again in memory, this mem table is also in memory, and then there is SS tables which persist on disk. Okay, and this SS tables is something known as sorted string tables. So I want to deep dive into each of them. So let's take an example. So let's say this table is representing the write operations that this database needs to handle. Now what we are going to do is, for every write that comes our way, we are going to insert this into a in-memory red black tree, which is basically giving us the sortedness. So it will be sorted on the keys, and this is a self-balancing tree, so the height will always be log n, and this is nothing but the mem table portion that we are talking about. So when Aman comes, Ram comes, Ankit comes, when we do these write operations, the tree would look something like this because it's balanced. Ankit is over here, and then Aman, which is going to the left side, it's here, and Ram, which is greater than Ankit, is over here. Now it will keep on, like for every write operations that are coming our way, it will keep on modifying this self-balancing tree. But once it crosses certain size, in this case let's say 3 is that size, so whenever there are 3 keys, it will basically persist that or flush this to hard disk, right? So this is a bit costly operation. Right now the writes were really fast, you are just playing in memory, right? So the writes are coming, you are writing them in memory, they reach some certain threshold size, in this case 3, you flush that to the hard disk, right? Hard disk can be SSD, HDD, I'm not going in that detail, but you flush that into the hard disk, a bit costly operation. But now when you are doing that, since this is a BST or binary search tree, it's already sorted by keys. So you can easily now iterate in ascending order of the keys and store these key value pairs in ascending order. And this is what the sorted string tables are all about, right? So I have told you the mem table, which is this in-memory red black tree. I've told about SS table, which are this. Right now, like there are only 3 entries, but it will be a lot, right? So you can say something like when it's several megabytes, at that point of time, we will do this flush operation. So for several megabytes, till that point, you are having really high throughput for write because you're just adding that to your BST, which is in memory. All right. So now you have flushed it over here, but what is this index? Now coming to that, let me magnify this example. Like right now there are 3 entries, but in a really huge segment file or a very huge SS table, which is like several megabytes, this is how it will be looking. Like the keys will be sorted because thanks to BST. So the keys will be sorted, and now I am dividing this file or this segment into several blocks. Each block is of size 10 KB, for example, right? And then I'm creating an index. Now this is in memory, okay? So this is kind of a sparse in memory index, and this will have again the same thing that we were having in the previous database, right? The append only approach that we were having, in which all the keys were there in the database or in memory. Now we will only keep the top of each block in this in memory sparse index. So from the first block Argentina, from the next block it's auction, and from the next block it's banana. So for several 10 kilobytes of data, only one key is there, right? So only one key per 10 kilobytes. So in this way, we have really cut down on this limitation that in the earlier approach, which was not on LSM trees, if the number of keys are really huge and they are not fitting in RAM, you could not have used, right? But now, since you're not maintaining every key in RAM, this limitation goes away. Only one key per 10 kilobytes, and these numbers you can tweak, right? So you got what's happening, right? So a lot of writes are coming your way. You are maintaining some in-memory BST, which can be a red black tree. And now once it crosses several megabytes, you flush that. It looks something like this. And then you create this in-memory index also, which is now sparse because not all the keys are over here. And the keys are over here for each block of 10 kilobytes. So for each block of 10 kilobytes, you are having the byte offset to the starting of that block, right? So Argentina is 0. So this is the start of file. And you know that the 10 kilobyte block is over here. Then for the next block, you can see that auction is the key. And for that, this byte offset is pointing to the beginning of the next block, right? Also, the good thing is if you want to search for, let's say, I don't know, ash, okay? So ash will come obviously in between Argentina and auction, right? So you do not even need to scan the entire file. Because keys are sorted, you exactly know which is that 10 kilobyte block that you need to search for, right? So you can directly jump to the offset of that particular block in which you feel this key should exist, and then you can read all the keys in that block, which is like reading just a few kilobytes is very fast. So you can read all the keys. If you found it, then you can return the value from the disk, right? So one thing to note over here is what will happen while you are doing this flushing. What if more write comes in your pipeline? So for that, what you can do is, once the in-memory tree is crossing that threshold and now you want to make the decision to persist this into some segment or SS table, which is on disk. While that is happening, you can now work with a new instance of the in-memory red black tree. So in this case, the first 3 writes, they completed the threshold, and while I am flushing this as an SS table on disk, the next writes can continue to happen on the next instance of the tree, and we can then get rid of the earlier one, right? So in this way, for Aman, Rohan and Sumit, this is how the next version of the in-memory tree would look like. Again, it will be balanced. So now since the size is 3, it's time for me to flush it. So I create a new segment, which is again an SS table sorted on keys, and I'm having the values, and I will create an index for this also, right? So once I create this and it's having a lot of entries, so which will look like this. I have a division into 10 kilobyte size blocks, and for every block the start of that key is there in the sparse in memory index, and in this way for every segment file I will have this sparse index as well. So now how will the reads happen? Well, if let's say the user wants to read Ankit, first thing that you want to do is read it over here, the in memory thing, because this is having the latest entries. If you find Ankit over here, simply return the value from here. Otherwise, now you have to iterate through your segment files or SS tables, and you will do that in the so basically always one segment will always be having a written timestamp greater than the previous one, right? So you can maintain a chain of these segments and you can iterate them in the descending order. So basically the latest written segment or SS table, you will perform a read for Ankit in that. In this case, Ankit is not present in this segment. So you say that, okay, I need to go to the next segment, which is this one. And you say, okay, I found Ankit over here. The value is 320 and you return to the user, right? So a read can be a little bit tricky, but writes are really fast because first of all, you are writing directly to memory, and that like there is no disk IO. That's terrific. And there is disk IO involved, but it's happening whenever your in-memory regulatory is crossing that several megabyte threshold. Alright, so writes are super fast, reads are kind of fast because we are not like wasting a lot of time. So let's say if this is several megabytes, I'm not reading all the keys, right? Because I know that this is sorted in ascending order of the keys, and I have this sparse in-memory index. So if I do a lower bound or upper bound on the searched key, I can directly find out which is that 10 kilobyte block that I need to search. Okay, so for every segment which is in megabyte size, I'm not searching it entirely, but I just for every segment need to search at max 10 kilobytes, which is a problem at this point of time, and we'll solve that. So like you are getting a lot of writes, you are creating that in memory tree, then keep on flushing that to new created SS tables, right? So each SS table is basically a file on disk, and over periods of time there can be a lot amount of SS tables that you generate, and the writes on same key might occur at different points of time. So the same key might be present in a lot of different SS tables. So this might lead to even space wastage, and we have discussed the approach on how to fix this problem, and similar compaction algorithm can be used here also. So since what you can do is you can from time to time you can run a compaction kind of process which will work on like it will pick some continuous range of 3 to 4 or whatever, like a lot of segment files or SS tables can be picked in one run, and you can compact them and generate a new segment file which is again sorted. So in this case Aman, if you can notice, it's occurring both in this segment and this segment, and obviously each segment file, like this segment file is created at timestamp T1, this is at timestamp T2. So obviously the latest value for the key Aman is 220 because T2 is the greater timestamp. So when you're doing the compaction, essentially what you can do is you can, since every sorted string table is obviously sorted on keys, you can kind of do what we do, like given a list of sorted arrays, you want to generate a new array which is sorted and it's having data from all the arrays, right? So similar approach can be used, kind of merge sort kind of behavior can be used here, in which you can start with the first keys on all the tables or all the segments that you want to compact, and whichever key is the shortest or the smallest one, you can put that in the newly generated segment and then repeat the process until you process all the files. So in this way it's very easy for you to generate this new compacted segment, which will again remove all the duplicates on keys because every key will exist only once in this newly generated segment. So you are also saving space and you are throwing away most of the segment files, and you're creating larger segment tables with periods of time. So what is the problem in this approach? Again, like I have mentioned this already, and we are in discussion of that topic, that reads are a bit slow, because what if a key does not exist, right? So you will do a mem table read, it will say that that key does not exist, and then let's say there are 20 SS tables for now, for example. Then you will go through 10 kilobytes in each of these 20 SS tables, which is again a waste of time, right? So because if the key had existed, it might happen that you found it in mem table or you found it in second or third SS table. But for keys which do not exist, like just to simply say the user, okay, we do not have that key, you are wasting a lot of time. So how we can fix this? Well, you can use something known as Bloom filters. Now, Bloom filters, they are a different data structure which are probability based, and they really answer very fast whether the key is present or not, and it's very space efficient. So if you want, you could have used for every SS table, you have used some hash map in which every key could have said that, okay, I am there or I am not. But since the complete idea is we are talking about very huge databases in which all the keys can't fit in memory, so that goes out of the picture. So that's why Bloom filters, they are very memory efficient. So I'm not going into the detail of Bloom filters, but just to give you an overview, I'll actually go through this site. So you can see that for Bloom filters, if it has m bits and k hash functions, the insertion and the search time space complexity is order k, right? So as I'm saying, like the number of hash functions is not very high, and in fact I can also have a look in that. So if you want like a million entries in your Bloom filters, and I'm talking about this data structure which is probability based. So if you want a 99% accuracy, for that you only need 1.14 megabytes of memory and only 7 hash functions. So I can say that you have simply order 1 query time in which it will say whether the key is present or not. Now it's not everything is magic over here. Obviously it's 99% accuracy. What does that mean? It means that if you ask a Bloom filter whether the key is present and it is saying that it's not, then it's definitely not present. However, if the Bloom filter is saying yes, that key is present, then it may or may not be present. Okay, so now when there is a key which does not exist, the mem table read is super fast, no problem. But now for SS tables, for each SS table, I'm going to create the Bloom filter as well. So when I was doing this, when I was flushing to hard disk and creating this SS table, and I'm creating this in memory kind of sparse index, I will also create a Bloom filter which will be very space efficient, and it will tell me very easily whether this SS table contains some key, right? So whenever user does some read, let's say the read is on 𝗜𝗥𝗘𝗣, I can very ask the several megabytes of SS table that, hey, use your Bloom filter to tell me whether this key is present in you or not. Okay, and there are around 6 or 7 hash functions, and the time complexity comes down to order 1, and in a very fast fashion, in this way I can get the answer that, okay, the key is not present, and I can move on. However, it might happen that since it's 99% accuracy, in few cases it might happen that you say the Bloom filter will say yes, the key is present, and you end up doing a read on 10 kilobytes of block, and it might happen that the key was not present. But again, the accuracy of 99% you can tweak around. So if you want more accuracy, you can decrease your acceptance threshold by 0.001. So now the 99.9% accuracy, and the space is just 1.7 MB now, and the hash functions are 10. So it's not that high, but the benefit is huge. So in this way, Bloom filter can be used for optimizations, and it's actively used. So the problems of reads in this way will go away for keys which do not exist. What about other thing? So for, let's say, 1000 entries, we are only doing in memory writes, right? Because only after, let's say, 1000 entries, we take a decision to flush it to disk. So it might happen that for the entries which are there in the tree, which is in memory, it might happen that there was a power failure and those writes are now lost, right? So if there is a crash, you are having data loss issue. So to solve this, what you can do is, for all the keys which are in the memory right now, which are not yet persisted as SS tables, for those keys, you can continue to use our old strategy of append only logs for the in-memory tree. So in this way, if there is a crash, you can use that append only log file to recreate this in-memory tree. Okay. So this is how I just wanted to discuss what LSM trees are and how they work behind the scenes. I hope I was able to give you a basically working idea of how they work. And now if you want to go through like the GitHub versions of RocksDB or easier implementations of LSM trees. I'll drop that in the description below. And now I think we have covered the log structured based storage engines, and now it's time to discuss B trees, which are page oriented, and we will see how they work and how they differ from log structured storage engines. But now the best thing is, after few of these, like 2-3 videos in which we discuss this log structured and obviously B trees, once we discuss that, the good thing is whatever fancy databases you hear like Cassandra or RocksDB or LevelDB, right, or Google Bigtable, now you would be able to understand or have a sense of like what is happening behind the scenes, how is data being stored on the disk, and how they are finally doing writes and how the reads are happening. So all these things, how you do it from scratch at the base level, I hope those understanding and those concepts is much clearer to you now. So I hope you enjoyed this video, and if you did, make sure to hit the subscribe button, like this video, and click on the bell icon so that you don't miss further updates on this series.